Good afternoon, everyone. Thank you for being here. I'm glad to present the optimization of shrinkage compensating fiber reinforced mortar for repair, part of my research at Missouri University of Science and Technology under Dr. Aghaee's supervision. The outline you see, I'm going to start with the investigation method, describe the factorial design and advantages, experimental method and results will be discussed, and the optimization method will be elaborated. An optimized mixture will be used for the repair, you will see, and I will wrap up with some conclusions. Investigation method was based on the design of experiment, which we consider the repair criteria, including the slump, compressive strings, fiber pull-out, and shrinkage. Microstructural analysis were done to figure out the relationship between the internal factors and output responses. One of the optimized mixtures was used to repair larger scale bins. So let's talk about factorial design. What's factorial design? Factorial design is a structured, statistics-based, and active regression approach to determine the effect of multiple variables on multiple responses. It aims to reduce the number of trials to figure out the relationship between the input variables and output variables, and reduce the number of experiments. So the advantages are the number of experiments, reduced number of experiments, the time and cost, and investigate the main effects and interaction of the variables. Also, it's very applicable to large number of trials and works very well when the number of variables are limited to 3. And reduce potential bias by randomizing the experimental runs. You have two types of factorial design, full factorial and partial factorial design. Full factorial considers all the combination of the possible variables and levels. However, partial factorial includes no less than one trial for a few possible combination of variables and levels. If you have n variables, x levels, say 3 variables and 3 levels, say minimum, medium, high level, we would have 3 to 3 number of combination, 27 combinations for full factorial situation. In this full factorial system, you can use coded values corresponding to low, medium, and high level of the factors, like -1, 0, and +1, as you see. If we remove one of the middle variables, say middle ratio of a variable, we would have interpolate between low and high, and we would have 2 to 3 combinations, which is 8, and the number of variables, the number of trials would be much less. I would like to talk a little bit about the materials I used in this study. Expansive agents, shrinkage-reducing admixture, and superabsorbent polymer, which are mainly shrinkage-reducing admixtures and internal curing by superabsorbent polymer. Expansive agent causes initial expansion, which reduces the later shrinkage. There are 3 types: CaO-based, MgO-based, and CSA-based. I chose the CaO-based because its high heat of hydration, initial hydration is quick, and less water demand, doesn't have later edge expansion, which is not desirable. Shrinkage, reducing admixture are non-ionic surfactant, which reduce the surface tension of pore solution and reduce the shrinkage. Superabsorbent polymer are polymetric materials classified into ionic, non-ionic, and cationic, and they absorb a lot of water and dissolve the water over time, gradually into the matrix. As you see on this slide, I used fractional factorial design. This is the mixture matrix, including 8 main mixtures, and you see the coded values, three first rows, and the absolute values. The relationship between coded values and the absolute values on the right. Coded value is equal to absolute value minus the middle ratio of that variable divided by half a spread of the variable. In factorial design, we are supposed to have central points to measure the experimental errors. I had 4 central mixtures, central points, designed based on coded value of the 0 or middle ratio of the variables. Also, we need to validate the models, but by validation points which are made up, which are designed based on intermediate values of the variables. I had 6 of them. In overall 18 mixtures instead of 27, which reduce the time and cost and easier experiment. I'm going to talk about the result, slump and compressive strength you see on this slide, mini slump. Using expansive agent and shrinkage reducing admixture reduced the slump. However, SRA improved the slump. On the graph, you see the compressive strength reduced by all the shrinkage mitigating materials, and the combination was the worst, up to 50% actually reduction in compressive strength. Derived countergraph from the statistical models are shown at the bottom. You see the best result was observed by the combination of expansive agent and shrinkage reducing admixture. However, I found that if we limit the coded value to middle value to 0, and we will get over 60 megapascal compressive strength after 28 days. Here is fiber pull-out strength result. As you see, the use of superabsorbent polymer reduced the bond strength, and that was due to the reason you see in optical microscope image. The particle absorbed a lot of water. In this case, was 30 gram per gram of superabsorbent polymer. So absorb a lot of water, swelled, and dissolve the water for internal curing purpose, and then leave voids into the matrix, which reduces the mechanical properties. The best system based on the countergraphs derived from a statistical analysis was the combination of expansive agent and SRA. Okay. I'm sorry. Okay, here you see the result of shrinkage initially and up to 56 days. I need to mention that I use embedded strain gauges for measuring shrinkage, which was mounted to data acquisition system and recorded data every 20 minutes. Each curve is the average of 2 strain gauges and 2 samples. And as you see, initially after 12 hours, totally each individual system compensated for shrinkage. However, the combination was better, and some mixtures experienced expansion. After 56 days, you see the bottom, the best individual system was expansive agent system. However, the combination was better, and even after 56 days, the combined system didn't have any shrinkage, and some of them were in expansion. The countergraph shows that, again, expansive agent and SRA was the best. However, the other system didn't experience a significant amount of shrinkage. Relative humidity was measured by sensors in the concrete, which pick up the relative humidity right after casting and up to 10 days. EA system absorbed a lot of water right after casting, and because the expansive agent wanted to form portlandite, and the chemical reaction needed a lot of water compared to the other system. However, SAP system desorbed the water into the system and had higher relative humidity over time. Microstructural characteristics are shown on this slide. EA system had a lot of portlandite deposition around the fiber in the middle and the aggregates, and micro cracks was observed in this system because of the excessive expansion due to the high content of expansive agent. SAP system, as I mentioned, left voids you see around the fiber, and that was the reason for the lower mechanical properties. Hydration kinetics showed that the EA system and EA combined with other shrinkage mitigating materials had the highest peak, shortest induction period, and short acceleration, deceleration period. On the other hand, SAP and SRA system, the lowest peaks and wider acceleration, deceleration period, and induction period. You see XRD result at the bottom table. SAP EA had a huge, large amount of portlandite, which justifies high expansion and a quick strength development. On the other hand, SRA mixture had high unhydrated C3S, C2S, which justifies the delay in strength development and hydration peak. MIP results are shown on this slide. EA mixture had higher total porosity, and as you see on the right, higher micropores. Comparing the 2SRA system with ref mixture, the 2SRA system had a larger amount of capillary pore, which is the function of related to the function of SRA, increases the capillary pore, reduces the surface tension, and reduces the shrinkage. Element mapping at the interface of fiber and matrix is shown on this slide. Fiber is FE is fiber, middle green circle, SI sand, CA portlandite, and C porosity. As you see at bottom right, the SAP system had a lot of porosity and low inferior mechanical properties, which we discussed. Optimization was based on the slump mechanical properties and shrinkage, targeting mechanical property the highest, and shrinkage and slump mediocre value, because we didn't want too high expansion and very much excessive shrinkage. Both causes cracking. The derived models are shown in the middle with pretty good R squares, and the optimized three mixtures were individual use of expansive agent, not at the highest level, medium level of expansive agent combined with either low content of SRA or low content of SAP. The properties also predicted for the optimized mixtures, as you see on the thing. One of the best optimized mixtures, including 5% EA and 0.5% SRA, was used to repair larger scale beams. The beams, except for the reference beam, were cast 2/3 with conventional concrete, and 1/3 the optimized concrete was inserted through the pipes. You see 4 pipes were embedded into the conventional concrete, and repair concrete inserted and filled the bottom tensile zone of the concrete beams. The beams were 8 feet long. Flexural properties of the beam was investigated, and as you see, comparing the identical beams, identical repair beam with the same amount of reinforcement with the reference beam, the repair beam had up to 48% higher first crack and 5% yieldless stress compared to the reference beam. And as you see, the area under the load deflection curve for the green compared to the black is much higher, indicating higher toughness for the repair beam. Here, more detail about that flexural test. 48% higher first crack load, 4% higher peak load, and 32% higher toughness. In summary, shrinkage mitigating materials limited to medium level investigated in this study, like 5% EA, 1% SRA, and 0.25% SAP is preferred to keep the good amount of good mechanical properties. The coupled effect of EA and SRA is preferred to have good mechanical properties and perfectly compensate for shrinkage. 10 EA mixture had high expansion, excessive CH or portlandite formation, and left micro cracks into the matrix and caused lower mechanical properties. Half SAP absorbed a lot of water and swelling the SAP particles, desorption, and leaving voids into the matrix led to lower mechanical properties. Multi-objective optimization showed that the individual use of expansive agent and medium level of expansive agent, either with low content of SRA or low SAP content, can produce flowable, high strengths, and low shrinkage concrete applicable to repair with enhanced flexural properties. These are the references, and thank you for your attention. I'm glad to take your questions.